saying thank you for the invitation, and yeah, such a great pleasure to be here for such a wonderful occasion. I've met Yael and Jonathan and Lisa all around 1994, give or take, which means, mathematically speaking, 30 years ago, which means mathematically speaking, like half our lives, which is give or take. So it's quite amazing and, well, scary, I don't know. So back in those days, we were mostly interested in symplectic geometry, moment maps, moduli spaces. And now, well, sort of we're still interested in the same things. Nothing much has changed, and I think we haven't changed much either. Not so much, at least. Okay, so yeah, I was going to revisit moment maps and Manin pairs. So the title of my talk refers to a paper by Anton Alexeyev and Yvette Kossmann-Schwarzbach in Journal of Differential Geometry. So the title of their paper is Moment Maps and Manin Pairs. That's that paper that I want to revisit. Anton, unfortunately, is not here yet. He's, I believe, in the air right now. But maybe it's better this way. Right, so it's about moment maps. So 30 years ago, we were mostly interested in moment maps in the sense of Fourier. So you have some manifold with group action. You have a symplectic 2 form on that space. And you have some equivariant moment map, taking values in the dual of the Lie algebra, satisfying certain axioms. So that's the classical theory. But yeah, around that time, about 30 years ago, people started experimenting with other moment map theories where, in particular, the target of the moment map gets replaced with something else. Right, so instead of just dual of the Lie algebra, we might consider other moment map targets. The 2 form, okay, sometimes it's symplectic, sometimes it's not. It's always symplectic in some sense. So it's always non-degenerate in some sense, but not literally. So it's what you might call quasi-symplectic. And yeah, theories were developed. So let me just make a table. Let's see what I have in mind here. So starting out with the classical theory of Fourier. So this was around 1970. The target of the moment map is G star. Typical examples for Hamiltonian spaces are the coadjoint orbits. Then various other examples. And then you have important procedures of taking products. And you can do a conjugation. By conjugation, I mean you take minus the moment map minus the symplectic form. Right, so that's the classical theory, which was very much developed. Then the next, the first kind of new moment map theory, I think, was due to Lu. Don't want to, now she's here, so be careful with the year, 89, 90, something around that. Maybe it's generous. So where you assume that your group is a Poisson-Lie group, so you need to have a Poisson structure on the group which is compatible with a group multiplication. And then she was looking at moment maps taking values in the dual Poisson-Lie group. And again, main examples were orbits, in this case called dressing orbits, various other examples, and then you also have products, and you have conjugation, just like before. Products you can take because it's a group. So features of this theory were already a bit different from the standard theory. In particular, the 2 form in this setting is not G invariant. It's still symplectic, but not G invariant. And when you take products, it's a little bit tricky. You don't just take the diagonal G action, you have to take some sort of twisted diagonal action. So it's a bit interesting in that regard already. Interesting anyway, of course. And then a few years later, in this paper with Anton Alexeyev and Anton Malkin, we introduced this theory of G-valued moment maps. So with applications to moduli spaces of flat connections. So where the target of the moment map is the group G itself. Basic examples are conjugacy orbits, conjugation orbits, various other examples, and then you have, again, procedures of products and conjugation. The theory of Alexeyev and Kosman-Schwarzbach aims to kind of unify these three basic moment map theories and put them into a common framework. And their starting point for doing this was to look at Manin pairs. So this is Alexeyev and Kosman. So they look at Manin pairs. D, G. So what is a Manin pair? A Manin pair is a pair of Lie algebras where D has a metric and G is a Lagrangian Lie subalgebra. Okay, so Lagrangian Lie subalgebra. And then they assume it integrates to the group level. So they would take.
Is it non-definite metrics?
Yeah.
So this is Lagrangian in the sense of.
It's a metric in the sense of non-degenerate symmetric bilinear form, invariant also.
Symmetric.
Yeah. Symmetric. Yeah. So it's Lagrangian in the sense of symmetric bilinear forms, maximal isotropic. And maybe I should give the main examples first. So, for example, you could take dg to be the semi-direct product of the Lie algebra with its dual, and then G sitting inside there. That will lead to the usual moment map theory. Then in the Poisson-Lie group case, you would, well, in the Poisson-Lie group case, Poisson-Lie groups are classified by Manin triples. So you have some dgh. And the dg is obtained by just taking dgh and ignoring the h. So in the third case, you take dg. Now, this time we have a metric on G, and you take D to be G plus G bar. And the subalgebra is the diagonal. So those three Manin triples should lead to those three theories. That was the idea. And the way they're doing it is, I have to go look here, you take your Q to be, so assuming everything integrates to the group level, you take Q to be G mod G. So you see that this sort of works. So in this case, if you were to integrate, you would get D as the semi-direct product like this, and then if you take D mod G, you get the dual of the Lie algebra. In this case, if you integrate, you get D is G times G, and then you quotient by the diagonal, you get the group G. And here, well, it doesn't always work, to be honest. In many cases, when it integrates to the group level, D mod G is isomorphic to the dual Poisson-Lie group, but not always. So small flaw in their theory maybe, but often D mod G is G star. G star being then identified with the group integrating H. Okay, so that was their theory. So you have Q equals D mod G. Ideally, I wanted to squeeze that into the table. Do you have space there? Not really. Okay, so you take your Q to be D mod G. Well, examples are again orbits in D mod G. But then what else? What are other examples outside those classical theories? So the problem is, at first, there are no other obvious examples. And at first, there's no way of doing any products or conjugation. So that's maybe the question. So other examples? What about products and conjugation? So at first, it seems like there's no way you can do this because D mod G is just not a group in general. Right? When we did products here, we took advantage of the fact that the target of the moment map is actually a group. And then we can take products. But if it's not a group, if it's just a homogeneous space, then what to do? So, and because of that, there's one reason, there were not really many other examples, maybe a handful of other examples of space with D mod G valued moment maps, but as far as examples go, this was maybe a weak point of the theory. But then suddenly, Pavel Cervera, I think 2015 paper, found that actually there is a way of taking products. Called fusion products, just like we did for the G-valued moment maps. Somewhat strangely, there's a way of taking products. And yeah, it's a bit tricky. So I was saying in the G-star value theory, it was already a bit tricky because you don't just take the diagonal action, you have to modify the action. In this theory, I forgot to mention, when you take products, you don't just sum the two forms, you have to modify the two form, even though you pass to the diagonal action. And in his theory, you don't just take the direct product of the spaces, you have to modify the spaces. So the motivation for our work was trying to understand this construction of Cervera. And what we came up with is the following explanation. So let me state that as a theorem. The reason why you can have these products is there's a one-to-one correspondence between, let's call them quasi-Hamiltonian spaces. Maybe we should just call them Hamiltonian spaces. M with D mod G valued moment map. I should have said G spaces. So one-to-one corresponds between these things on one hand and quasi-Hamiltonian G times G spaces with, let's call them curly M, with D valued moment map. At the moment, it doesn't mean anything yet because I haven't really defined what these Hamiltonian spaces are for the generalized moment map theories, but I will get there. I haven't explained yet what it means in the Alexeyev-Kostman theory either. But I will do that in just a moment. But the idea is that there's a one-to-one correspondence between two different kinds of moment map theories with D mod G valued moment map and D valued moment map. And once the moment map takes values in D, well, we're in business again because D is a group, then there's a better chance of taking products. And the correspondence on the level of space is actually very easy and silly. So if you have this curly M here, you just take the quotient. So you just get rid of one of the G factors of the action. Okay, so any questions at that point? No, it's a quotient just by the, so we have a G times G action and we're quotienting by one of the factors. So the other action is still there. It's just very simple. So in one direction, we just quotient on the right by one of the G actions. In the other direction, if you have this space, maybe I can explain this. We have the moment map taking values in D mod G. There's a principal G bundle over it, and we just pull it back. So that's what we do on the level spaces. It's just very, very simple. But one has to explain what to do with two forms and so on. Yeah?
The right column, is that part of the mean pair sort? Is the G cross G and the D value going or mean pair for?
Is there what?
Is there any, does the G cross G action relating to the D value going
So there's a Manin pair for that one. So I will explain the statement. So we have to explain everything, especially we have to explain what it actually means to be a moment map and all that. Because I haven't even introduced this kind of theory yet of D-valued moment map. So it's not the AMM theory, because if it was AMM theory, then it would be Hamiltonian D spaces. But here we have G times G spaces. So I have to explain what these more general moment map theories are. So let's do that next. So looking at generalized moment map targets. Okay, so starting point is Manin pair. DG is given as in the AMM, as in the Alexeyev-Kosman theory. Then we say moment map target is a G manifold Q together with an extension of this G action to a D action. Okay, should also include the dimension of Q should be equal to the dimension of the group, and with a compatible D action, so Lie algebra action. So by compatible, I means we have a G action already, so the Lie algebra of G acts, and it should extend that Lie algebra action. And I want this Lie algebra action to have Lagrangian stabilizers. So these are the moment map targets I'm going to consider. Which includes the moment map targets that we've seen so far, but it's actually slightly more general. So examples would be for example, you can take Q equals D mod G, right, with the Lie algebra action of D from the left. But instead of this G, you could also take any other Lagrangian subgroup. You could just replace it with some G prime. Also, right, G prime is any Lagrangian D subgroup. It doesn't have to be equal to the G from the Manin pair. That works as well. And also in the Poisson-Lie case, you can actually now take Q equals G star, so long as the dressing action really lives on G star, if it exists. Because there's a way of writing down the Lie algebra action of D on this space, even if it's not of the form D mod G. So now it literally fits into this general framework. So it's going to be a very mild generalization of these Alexeyev-Kosman settings. Okay, so that we need. In order to write down formulas, we also need a splitting. Okay, so we choose an isotropic splitting. I'm saying this map has Lagrangian stabilizers, and I'm going to choose a splitting of that map. So TQ goes to Q times D. So isotropic means that the range of the splitting will be Lagrangian. It boils down to saying that, well, this action has Lagrangian stabilizer, so there's some Lagrangian subbundle in there, and we just choose a Lagrangian complement. So you have this splitting, which I can view as a one form. So it's a one form on Q with values in D. So that's an ingredient that I'm going to need. And using the one form, we can build a three form. Let me just call it Chern-Simons three form, but it's not really Chern-Simons construction. Which is given by the formula 1/2 minus 1/2 d alpha inner product alpha minus 1/6 alpha. So it's the same formula as for Chern-Simons, just not, in some sense, the transgression construction. At least I don't know how it's related. So this is then a three form on Q. So this kind of splitting, we need to choose in order to write down our axioms. So there's a one form and a three form once you choose the splitting. And then what are the axioms for quasi-Hamiltonian spaces? Quasi-Hamiltonian G-space with Q-valued mode map is well, first of all, it's a G-space. The mode map should be G equivariant. Right, we have a G action on Q and we have a G action on M, and the mode map should be G equivariant. And it's given by a two form. Such that the following three axioms are satisfied. The differential of the two form is minus the pullback of the three form. Three form that I introduced. The contraction with generating vector fields is minus the pullback of the pairing of this Lie algebra valued one form with Xi. So this is for Xi in G. And then there's a kind of non-degeneracy condition which says that the kernel of omega intersect the kernel of T phi is equal to 0. So this is the general definition. Any questions about this? Correct, yeah. Yeah. So maybe I should say that first. It reduces to all the standard mode map theories, of course, in particular to the group valued mode maps. So example is if you take your Manin pair to be used G plus G bar, the diagonal, then for one thing, we have to write down the splitting. So there should be a one form on the group with values in G plus G bar. And it's given by the formula 1/2, where is it? Right and left marker tau form. I think it's this. So in the first entry, you put the right marker tau form with the sign, and the second one, you take the left marker tau form. You can then check that it's a splitting for the action, for the G times G action. And then you calculate what the three form is. Oh, I forgot to say one important thing. The reason why you choose this combination is, of course, that this three form ends up being closed. That's the key point why you take this combination. And the 3 form in this case is what we call the Cartan 3 form. The left Mercantar form, inner product with bracket. And then these axioms are the usual axioms for group valued mode maps. Yeah, but in loose theory, there's also some alpha that one can write down, which basically, the alpha you can sort of read off from how the mode map condition reads. You kind of know what it's supposed to be. So there's some alpha in the story, and then it's again these axioms, and it turns out that this last condition in that case actually implies that omega has to be non-degenerate. And even in the classical theory, of course, there's again, classical theory after all is a special case of loose theory. There's some standard alpha that one can write down, and even though you write the non-degeneracy condition in this way, it turns out actually it is non-degenerate on the nose. Right, what else can I say? So maybe some remark is that symplectic reduction works for this setting. Right, so the usual thing, you take symplectic quotients. So for any element lambda in our mode map target. That's for the general setting, yeah. You always have symplectic reduction. You take the preimage of some value, you quotient by the stabilizer, and so long as the action is nice, it's going to be symplectic. Say again? Oh, yeah, of course, sorry. Oh, thank you. That was the contraction of the 2 form. That's the mode map condition, sorry. Okay, so we have our setting. We now know basically what these things mean. Let's explain in detail what I mean by these d-valued mode maps. Ready? A nice chalk. There's a nice chalk. Okay, so if you have any Manin pair, then you can just double it. Like this. This is then a new Manin pair. And the group now is G times G, right? Integrating this thing, and the Q I can take to be G, D. So this is what I mean by these G times G spaces with d-valued mode map. So there's one G acting from the left, the other one from the right. Maybe I write this down.
What is this in the case of ordinary Hamiltonian G spaces? What is this G cross G space?
Yeah, I haven't actually investigated, to be honest.
I've never heard of such a.
Yeah, so you could take an ordinary Hamiltonian G space and lift it up to a G times G space with a mode map, taking values in this. Yeah. Yeah. I'm not sure why one would do it, but in principle one can, yeah. Yeah, I'm not even sure. Kind of, yeah. But it's here viewed as a group. Hmm? I don't think it's that. I don't think it's that. You have a symplectic group part, but it's not like you have moment maps taking values in T star G. I mean, T star G is a symplectic group part sitting over G star, but I don't think one considers maps going to T star G. Anyway, where was I? Oh, I wanted to explain there's also another kind of reduction that one can consider. So, not to be confused with the symplectic reduction that I had over there. So we can look at the reduction of Manin pairs. Namely, if you have any Manin pair DG, consider some co-isotropic subalgebra which lies between G and D. So this is supposed to be a subalgebra. So if you have a co-isotropic subalgebra, then it's easy to see that its perp is an ideal. And so you can take a quotient. You can define D prime to be C mod C perp, G prime to be G mod C perp, because C perp, of course, is inside G. And in this way, you can reduce your Manin pair and get a new Manin pair, D prime, comma G prime. And if everything integrates nicely, then you can do the same things for the groups and the Qs. Right, you could then form also the corresponding, the group D we don't need, but we need the group G prime. So that's if we assume that the Lie algebra C perp integrates to a closed subgroup, so a bunch of assumptions in here. And likewise for the moment map target, we could take a quotient. No, C perp. Right, we want this to act on here, which again works if things are nice. So I assume it acts freely and properly. So that this is a manifold again. And in this kind of situation, so we can state our theorem like this. There's a one-to-one correspondence between quasi-Hamiltonian spaces, G spaces with Q-valued mode maps, and quasi-Hamiltonian G prime spaces with Q prime valued mode maps. You can go back and forth between them. So this is kind of the more general statement that we have, which implies this correspondence between D valued mode maps and D mod G valued mode maps. Because you can get D comma G as some quotient in the sense of D plus D bar comma G plus G bar G. Right, are we in time? So maybe we should just explain this. So an example of this is if you take this D plus D bar, G plus G as your Manin pair, and then you take C to be, what is it, D plus G. Then C perp is going to be 0 plus G. And then if we take the quotient, okay, so the Q in this case is the notation is sort of doesn't quite fit, but if you take the quotient of D by this group, we get D mod G. So we get from the D value theory to the D mod G value theory back and forth. I don't have time to explain how one actually proves it, but it's probably not so hard to imagine that one can prove things like this, right? You just take two forms, pull them back, modify it a little bit. One has to mostly keep track of this non-degeneracy condition, that it survives, but it all works.
Is there any sense for this corresponding to the one you just raised, like the categories? Is there like or anything like that?
Well, what this correspondence is a special case of is it's a Morita equivalence. It's a Morita equivalence between two moment map targets, and you can have more general Morita equivalences like that. So this is one special case that comes from taking quotients. Yeah, but it fits into this general setting of Morita equivalence, so that, for example, the theory of Hamiltonian loop group spaces is Morita equivalent to quasi-Hamiltonian G spaces, because the moment map targets are in some sense Morita equivalent. Or symplectic cross sections can be viewed in this setting, and so it's all part of that.
So in this theorem, is it also, like before you were saying on the level of manifold, it's very easy. Is it something just similar more generally?
Yeah, it's not quite as easy because you have to keep track of the two forms and non-degeneracy.
Just the manifold part, just the manifold part.
Yeah, the manifold part is just the same. Yeah, yeah. So yeah, if you have here the M, then the M prime is just M mod C perp. And pulling back, so yeah, on manifold levels, it's very easy. And by the way, we're not actually proving it on the level of two forms and so on. It's all phrased in this framework of morphisms of Manin pairs, but Manin pairs in the sense of current algebroids and Dirac structures. But yeah. So it's a relatively elegant proof, but don't have time to get into it. I want to spend a little bit of time saying a few more words about devalued mode maps, because I think I only have 50 minutes, right? So I shouldn't spend too much time. Oh yeah, so for one thing, I should now explain why does one have fusion for these devalued mode maps. So this is now for our devalued mode maps. So there's a fusion operation. If you have two spaces with devalued mode maps, call them M1 and M2, and I want to define the fusion product. What we do is, well, it's not quite the direct product, but not much harder than that. So we take the direct product, but we need a G times G space. This at the moment is a G times G times G times G space. So what we do is we divide out the diagonal action in the middle. So in this space, we get rid of two of the G factors, and then it becomes a G times G space again. And one can show that the two form descends and everything is good, and then the moment map descends to D, so it's just a map phi of some equivalence class x1, x2 is phi of x1 times phi of x2. And what we're taking advantage of is that when you take products like this under this diagonal action, it just doesn't change. You multiply by G inverse here and by G here, and so it just cancels out. So it descends. All good. So there's a fusion operation because of that. And there's also conjugation. Let's call it M star. Well, M star is just M itself. You just switch the two G factors. And the moment map, you take the inverse. So in this D-val series, it's very easy to do these products and conjugation, and then you can take the quotient by G and translate back to what you have there. But in some sense, maybe one shouldn't even, one should just stay upstairs. Right, and finally, I wanted to give some sketch of examples. So I was saying that there wasn't so many examples of these D mod G valued mode maps. But now if you think in terms of D valued mode maps, it's very easy to come up with lots of examples for moduli spaces. The curly M in the classical case? Yeah, I mean, not sure much there's to say. So we'd, so in general, you have your mode map taking values in D mod G. And you just pull it back to D. So I guess since in this case just a direct product, the curly M would just be a direct product in the classical case. And I don't even think you do anything special with the two form. I think you just pull it back. Right, examples. So examples come from moduli spaces. And just draw a picture. So it comes from moduli spaces on surfaces, but with bicolored boundary. So we have some, I'm going to color some portions of the boundary in red. There's some red segments here. Red stands for G, and white stands for D. So there, these vertices, these base points where the edges end. I need some here. So every boundary component should have at least one of these red ones. And then we can look at our space. It's going to be the set of homomorphisms from the fundamental groupoid into D, such that, so this is the fundamental groupoid. So meaning homotopy classes of paths between these vertices. And having a homomorphism from pi into D just means to each such path you associate an element of D in such a way that when you concatenate such paths, let's say these two paths I can concatenate, then you just take the product. So it's homomorphisms like this with the property that kappa of a red edge lies in G. And no quotient. So any such space will be a quasi-Hamiltonian D to the R space. Quasi-Hamiltonian, sorry, G times G to the R space with D to the R valued mode map. The mode map corresponds to taking the values at these white segments. The white ones are D. So for you can. Oh, no, on each boundary, I want some red segment.
No, but can the segment be the whole loop? Can the boundary be entirely?
Entirely red.
I'm trying to see if I can.
Yeah, I'd like to avoid it. I'd like to avoid it at this stage because I want on each boundary, I want at least one vertex also.
Is there a way of seeing the ordinary model space of connections?
Oh, so what I can say is, if you don't impose this condition, then this would be an ordinary quasi-Hamiltonian D space.
That would be the, but say if you want to do flat connections for G.
Yeah. Yeah, then I would do a similar thing. I would not have anything like this and say homomorphism from pi to G.
So G.
Yeah, but I don't do any colorings. But in this world with the G times G spaces, I want these colorings, and the point is that every white segment, which corresponds to a copy of D, has two endpoints on which a copy of G acts, so that's the G times G action. And so these are all examples. And okay, so I'm running out of time, so I just want to say in terms of these pictures, it's easy to visualize what fusion and conjugation and reduction does. So fusion is the following operation. So you have, that's my red. You have some part of the surface coming like this. So here's D, here's G, and you have another part coming in. Then fusion should basically replace D times D with D. And the way it does that is that it kind of glues in a strip like this. And this will be the new surface. And then this vertex disappears. So you can imagine you have these surfaces with boundary, and you kind of glue in some kind of bicolored strip. One side is white, the other one is red. Yeah, sort of, yeah. So that's what fusion does, and maybe just reduction, I want to say. Last thing. I mean, conjugation is sort of boring, it's just orientation change. But reduction is maybe fun too. So reduction, if you have some D, which is adjacent to some G's, what reduction is, just get rid of this D. So it just gets replaced with this. Okay, I think that's enough. Thank you.
Okay, questions? Yes.
So as you know, there are sequential generalization of values where that last value, the Dirac value was from the
Oh, yeah. So these, I hadn't used this language, but these Qs, I mean, over the Q, we actually have a Dirac structure. That's what's happening here. Yeah.
Is there an indication that you could generalize fusion product the more general
I think one would have to think like what exactly one needs to define fusion. We haven't really thought about that, yeah.
Other questions? Yes.
Your original A&M paper had this equivalence from standard moving maps to loop groups.
Yep.
Anything like that here?
Yeah, you can do that also, yeah. So you can look at moduli spaces of flat D bundles over the surface such that the restriction to these red segments has a reduction of the structure group to G. And so there's also a general theory that one could develop in principle of like some sort of Hamiltonian, it's not really loop groups, because it's not really loops that one is dealing with, but some infinite dimensional groups that play the role here of loop group. Yeah. So it's basically the gauge group of the boundary for this setting. So maps from the boundary into D, which over the red segments take values in G.
Other questions? Yes.
What happens if there's no boundaries there, like the moduli space flat connections, like
Yeah, of course, this wouldn't be interesting if I want some D-valued mode maps, but yeah, I mean, there are various other things you can do. By the way, you could have boundaries which are entirely red, then I would have to take some quotient by G there. One could introduce some other colors. This was very much done in, well, started by Pavel Cervera, and then Leblanc Cervera have done things like this with lots of colors. And then you could have also no boundary at all. Then you're back to the usual theory of moduli spaces of flat bundles. But then you don't see any mode maps anymore, and the spaces usually become singular.
Other questions? Yes.
Can we generalize theoretical quantitation for quantitation with delta theory in graphics?
Certainly not me. I mean, for the G-valued mode maps, I had done something like this with push forward and K homology and so on. But for these more general things, I wouldn't know. I mean, there's a bit in the direction of some sort of quantization with Hopf algebras and so on in the work of Leblanc and Cervera. So this things I don't understand very well. And yeah, one certainly doesn't consider quantization commutes with deduction in that setting. So yeah, I have no idea.
Other questions? Okay, if not, we'll resume at 10:30, and I have it on good authority that there's coffee outside. So help yourselves.